Hello everyone, I am Giridhari Deogharia, Assistant Professor of Mathematics in the Department of Applied Science, Haldia Institute of Technology. Today I am going to discuss about the third lecture of infinite series. In the first and second lecture, I have discussed about the basic concept of sequence and series and some convergence test. Today I am going to discuss about the alternating series and Leibniz theorem related to alternating series. And absolute and conditional convergence and its example. First, let us recapitulate the lecture 1 and lecture 2 with its key concepts. This is the key concept of lecture 1, where we have given the basic definition of infinite series. After that, we have introduced two standard series, which are geometric series and P series. A geometric series can be defined as in this form, where the first term is a, the second term is ar, and the third term is ar square, and so on. Here, if we take an example, 1 plus 1 by 2, 1 by 2 plus 1 by 2 square plus 1 by 2 cube plus dot dot dot. Here we can see that 1 by 2 is multiplied by each of the term. So the common ratio r will be 1 by 2 here, which is less than 1. Now this type of geometric series will be convergent if mod of r less than 1, and will be divergent if mod of r greater than equal to 1. Here r is equal to half less than 1. So this kind of series is actually a convergent series. Now a P series can be expressed in this form, summation of 1 by p. This can be written in this form, 1 by 1 to the power p plus 1 by 1 to the power 2p plus 1 by 1 to the power 3p, and so on. This type of series will be convergent if p greater than 1 and will be divergent if p less than equal to 1. So if we take an example, 1 plus 1 by 2 plus 1 by 3 plus dot dot dot, then here p is actually 1. So this is falling in this criterion. So this kind of infinite series is actually divergent. So after that, we have discussed about the comparison test of type 1 and type 2 also. Now we have discussed earlier about D-Alembert ratio test. This is a mistake. So if n is a infinite series of positive terms and limit n raised to infinity n plus 1 by n is L, then this type of convergent series is actually this type of series will be convergent if L less than 1 and divergent if L greater than 1. For Cauchy root test, this limit will be n tends to infinity n to the power 1 by n. Previously we have discussed about this with some examples, and for Rabbit test the limit term will be n tends to infinity n into n by n plus 1 minus 1 is equal to n. But the given series will be convergent if L greater than 1 and will be divergent if L less than 1. Now we are going to discuss about the alternating series. A series in which the terms are alternatively positive and negative. A series in which the terms are alternatively positive and negative. So the first term is 1, the second term is minus 1, the third term is 1 by 3, and the fourth term is minus 1 by 4. That's plus minus plus minus. That's why it is said to be an alternating series. This can be also written as minus 1 to the power n minus 1 by n. If n equal to 1, the first term will be 1 into 1 by n. The second term will be 2 minus 1, that is minus 1 by 2. The third term will be plus 1 by 3, minus 1 by 4, and so on. Now, with the help of alternating series, we can establish a theorem which is called Leibniz test. The alternating series minus 1 to the power n minus 1 an converges if the sequence n is monotonically decreasing. The first criteria is the sequence an. The sequence n will be monotonically decreasing and the limit of n tends to infinity n. The limit n tends to infinity n will be 0. So this is the mistake here, n is not there. The limit n tends to infinity n will be equal to 0. Now let's check and convergency of a infinite series 1 minus 1 by 2 square plus 1 by 3 square minus 1 by 4 square and so on. So the nth term will be minus 1 to the power n minus 1 by 1 by n square. Yes or no? Let's check. If n equal to 1, the first term will be 1. If n equal to 2, the second term will be 1 by 2 square. If n equal to 3, the third term will be 3 square and so on. So this is a correct nth term of this alternating series. Now checking whether the sequence n is decreasing or not. So first take the an value which is 1 by n square and the an plus 1 value which is n plus 1 square. Now an minus an plus 1 minus an will be actually n plus 1 whole square minus 1 by n square. This will give minus of 2n plus 1 by n square into n. This is negative because n is positive here. So n plus 1 is actually greater than n. So the next term is always less than the previous term. That's why it is a decreasing sequence. This is a decreasing sequence. This is a decreasing sequence. Again, limit n tends to infinity 1 by n square is 0. So by Leibniz test, this is actually a convergent series. By Leibniz test, it is a convergent series. So these are the basic exercise. This is very important question. I will give a hint to solve this kind of problem. Here cos n pi is nothing but minus 1 to the power n. So this is actually a alternating series. So you can apply Leibniz series. Now we are going to discuss about the absolute and conditional convergence. The absolute and conditional convergence. An infinite series n of real numbers is said to be absolutely convergent if the series mod of n summation mod of n is convergent. Again, if the series n is convergent but the mod of n is not convergent, then it is a conditional convergent series. Now again we are repeating the same definition. An infinite series summation n of real numbers is said to be absolutely convergent if the series summation n is equal to 1 to infinity mod of n is convergent. Again, if the series n is convergent but the series mod of n is not convergent, then it is conditional convergent. Now taking this infinite series which is absolutely convergent or not. So this can be written as in this form. Now taking a, the sequence a will be this. The first term will be 1, the second term will be 1 by 2, the third term will be 1 by 3, the fourth term will be 1 by 4, and so on. So this is actually greater than. So this is a monotonically decreasing sequence, monotonically decreasing sequence, and again limit 1 by n tends to infinity is 0. So by Leibniz theorem it is convergent. But if we take the mod of A means the summation of 1 by n. Summation of 1 by n means 1 plus 1 by 2 plus 1 by 3 plus 1 by 4. So this is a actually standard series. This is a P series, and the value of P is 1. And if from P series, if the value of P is 1, then the series will be a divergent series. So here the main series is convergent, but the mod of that series is not convergent. So this is a conditionally convergent but not absolutely convergent. Conditionally convergent but not absolute convergent. Why not absolute convergent? Because here the mod of n is not convergent. Mod of n convergent mean. अगर mod of the n convergent हो जाता, it will be a absolutely convergent. Okay, यहाँ पर mod of n यहाँ पर नेगेटिव चला जा रहा है, तो क्या होगा? Actually a will be 1 by 2. So that's why it is a divergent series, not convergent, and because of this, it is a conditionally convergent series, but not a absolutely convergent series. So these are some examples. This is a very important question, and this is also a very important question. We all know that cos of n pi is -1 to the power n. So this is a alternating series, and this is also a very important question. So thank you. Your overall series of lectures about sequence series is over.